Okay, welcome to our last talk in this track. And so we'll have Pekka Latvala from the Finnish Geospatial Research Institute. And he will tell us something about using Python for improving geospatial data discovery. So, Pekka, please go ahead.
Okay, so good afternoon, everyone. My name is Pekka Latvala, as you said, and I work in the Finnish Geospatial Research Institute that is part of the National Land Survey of Finland. And I'm going to talk to you about how to use Python for improving geospatial data discovery. This is the agenda of my presentation. So first I will talk about the AquaInfra project in general, that this work is done as a part of. Then I will introduce you to the AquaInfra architecture. And finally I will talk about the ontology search in the AquaInfra data discovery and access service. So the AquaInfra project is an EOSC project that is a European Open Science Cloud, and it started in last year in 2023 and it will finish in 2026. So we are now about 1.5 years into the project. We have a consortium consisting of 21 different partners from 10 countries. And here you can see the spatial distribution of the project partners in a map interface. So we have partners from Austria, Denmark, Estonia, Finland, Germany, Latvia, Malta, Norway, Spain, and United Kingdom. And the AquaInfra project aims to develop a research infrastructure that contains fair data and services that support the research activities in marine and freshwater domains. So in principle, we are creating a spatial research infrastructure for water domain. This is the overall architecture picture of the AquaInfra architecture. So here we have an AquaInfra data space, and it contains a data discovery and access service that uses the Geo API and also a CKAN application. And this data discovery and access service provides federated metadata search and data access to various background services. And it contains also a local metadata repository. There might be some datasets that don't have services available. Only, for example, like they have like data in, for example, in a file. So we can use this local metadata repository to save the metadata of that dataset and serve the dataset through the APIs. And this DDAS contains also an ontology search component that supports these metadata queries. And we have defined 3 different data zones that the data can be refined to. So in the bronze zone, we are providing the data in a raw format. And silver zone, it is harmonized data. And in gold zone, we are providing transformed and integrated and analysis-ready data. So the DDAS metadata service, you can use the following background services. So we are providing access to OGC API, OGC Catalogue Service for the web, so-called CSV services, then OGC API Records services, and then we also can provide access to custom APIs. And for that we have to write custom data provider plugins. And then the output of this metadata search is the OGC API Records interface. And then for the data access part, we provide the features and OGC API coverages interfaces. These are currently the services that has been connected to the metadata search. So for the OGC CSV services, we are providing access to Arctic data center services and Copernicus land and marine services. Then we have datasets from the Center of Environmental Data Analysis, EMODnet, Helsinki Commission, International Council for Exploration of the Sea, and INSPIRE, and joint CETASEAN data program, and ODIMS and Finnish Environmental Institute datasets. And then we also provide access to custom APIs. These are, for example, WISE freshwater datasets and global biodiversity information facility datasets and Blue Cloud. And then we also have some data in the locally stored CKAN application. And these are Corin Land Cover Plus, EU Digital Elevation Model, EU Hydro, Euro Regional Map, Hydrography 90 basins, WMO river networks, and WMO basins. And then if we go forward in the architecture picture, there is on top of the DDAS service, there is an AquaInfra interaction platform that provides a user interface for the DDAS services. So there is a search functionality and data access, but there is also a virtual research environment, and that contains functionality, for example, for creating workflows for different kind of data analysis. And then we are also integrating these services to the EOSC services, and we are providing interoperability with the digital twins of the ocean projects. And finally, we have the users as a scientific community, and we are aiming to provide scenarios for 4 different use cases. This is a screenshot of the interaction platform. So this provides a search functionality for the DDAS services, and the ontology search will be integrated in this search functionality. And this is the virtual research environment. So this has been implemented with the Galaxy application. And I think the Galaxy application comes from the genomic research field. And it's this kind of computing environment that can, for example, give access to R scripts and Python scripting. And you can also run different applications, for example, QGIS with that. And now to the ontology search. So the purpose of the ontology search is to improve the DDAS metadata searches by providing related term suggestions to the user's original search terms. And these related terms are searched from ontology or thesaurus data. And here user can select and include the appropriate terms to the metadata searches. So this is an example of the workflow, how this could be used. So user could search, for example, the term river, and this executes the normal DDAS metadata search together with the ontology search at the same time. And then the user gets the results for the normal metadata search and a list of related term suggestions that could be included to the search. And then the user selects the appropriate terms that he wants to include to the search, and the search is executed again with also the added search terms. First we did some inventory of potential ontologies and thesauri in this project. So we went through a number of different ontologies and thesauri. So we went through Eiffel ontology, and these consist of 3 domains. There are essential climate variables, sustainable development goals, and Earth observation. but this contained only some relevant classes for our use cases. And then we went through ocean data ontology, and this was also found not to be very relevant for our uses. And next we went through in-water sense ontology, and this was mostly focused on different sensors and sensor data, so this wasn't so useful for us either. And then we investigated surface water ontology, and this contained various feature types and water body types. And next we went investigating natural resources and environment ontology, and this is available in Finnish and English. And this contains actually quite a lot of concepts, and something like 60 concepts that are relevant to hydrography. And then we went through various thesauri. So we investigated the USGS thesaurus, UNESCO thesaurus, UN BIS thesaurus, and Acrovoc multilingual thesaurus. And finally, we investigated the general multilingual environmental thesaurus. And after doing the investigation, we decided to go forward with the project by using this GEMET thesaurus, and it was selected as a starting point for the implementation work. And this GEMET contains terminology in many different languages, so there can be terms written with up to 37 different languages. And we decided in the work that we are limiting the project only to English language. And the English terms in GEMET can be written either in English or American English writing. And there is an example of concept. So this GEMET data consists of concepts, and they may have preferred labels or alternative labels written in multiple languages. And there are examples. So there's an ASCOS pref label with the language tag at the end, and also alternative label written with a little bit different spelling. And these concepts, they may have links to other concepts. The relations may be modeled using broader, narrower, or related relations. And they may have many broader, many narrower, and many related relations. So here is an example of one GEMET concept, how it is represented in the hierarchy. So we are interested here now in the river basin term. So it has narrower concepts: international river basin, river basin management, and river basin development. And the river basin management has yet again the narrower concepts: international river basin and river basin management. So here we can see that these labels or concepts, they don't have a strict one place where they are in the GEMET hierarchy, but they can be represented in many different places. And these then have related terms. So river basin has a lake basin related terms that has his own broader, narrower, and related concepts. And then there is a broader concept, hydrographic basin, that has yet again other narrower concepts and related concepts, and yet again more broader concepts. And these show the themes in the GEMET thesaurus. So we are mainly interested in this project of water-related terminology and also socio-economical terminology. So these themes contain terminology that are water-related, and these might not be strictly water-related, but there may be also like pollution that is indirectly water-related. And it also contains themes that contain socio-economical terminology. Then we did a web service implementation. So we are using a Apache Jena Fuseki SPARQL server as a data store. So this contains a triple store where we can load the ontology and thesaurus data in a RDF format. And then it contains also a SPARQL endpoint where we can make queries to the RDF data in a SPARQL format. And then we created the ontology search API web service. This was implemented with Python, and we are using Django REST framework, NLTK, and SPARQL wrapper libraries. And the output of this service is provided in JSON format. And these are the parameters that are used in this service. So the keyword is just the search word. And then we have broader, narrower, and related parameters. And broader parameter works so that we are including only the first immediate parent of the find matches to the output, because it very easily goes to very abstract level from the actual match that we find. So we take only the first parent into the output. A narrower parameter takes all the narrower concepts of the originally found matches to the output, because they are always relevant to their parent concepts. And the related parameter works so that we are taking all the related concepts, and if it is used together with the narrower concept, we are also taking all the narrower concepts of the related concepts to the output. And then we categorize the results into 4 different groups. So there is the original match, narrower, broader, and related. And then we perform some morphological analysis to the input words. So the GEMET data consists mainly of basic forms of the words. So if we want to use also, for example, plurals, we might want to find the basic form of the plural input word. So we are using this Python library NLTK for performing this morphological analysis, and it contains different approaches to doing this. So there are functions for doing the lemmatization, and this uses a dictionary for performing the word transformations. And then there are stemming approaches that use rules for transformation. And we did a comparison of different functions in the NLTK library. And based on this investigation, the WordNet lemmatizer is the best of these approaches. In our case, it cannot lemmatize properly input words that are consisting of 2 different words, but we can get rid of this by splitting the input into 2 different words, and we lemmatize only the last word. So then we get also these red rows. We can handle them properly also. And when we are doing the SPARQL queries, we are making them with both forms together. So the original form and the lemmatized form. So for example, the plural form and the or the singular form, because some of the GEMET concepts are provided also in plural form, although most of the concepts are written in singular form. So here are some examples. So here we are searching for concepts that match with the term lake, and we get as a result 4 concepts with different labels. And here we are not taking any broader related or narrower relations into account. And then we remove if there are any duplicate labels in the output, remove them, and we get here in this case we get 4 terms as the output. And another example with the same keyword, lake, but now we are taking also the related relations into account. So we get the same 4 concepts as a result, and 2 of these concepts have also related concepts in the geometadata. And again, we remove possible duplicate label names from the output, and we get 8 terms as an output. Then we have a test user interface implemented. I can show this actually in a live situation, live demo. So this is just a demonstrative application. This is not how it will actually use when it will be integrated into the interaction platform, but this can show the functionality. So we can here select if we are taking the narrower, broader or related terms into account. And we can, for example, here search, for example, lakes. We are performing search. And we have colorized these terms now with different colors based on their relations. So the blue ones are the original matches for the lakes keyword, and the light blue ones are the broader relations. Yellow ones, orange ones are narrower, but in this case there are none of those in these matches, and the brown ones are the related ones. And this would work so that we can select here the terms that we want to include to the metadata search, and then we just select them and they would be added to the metadata search. And then we can also search, for example, quite generic terms. So for example, agriculture, and here we would get lots of narrower concepts as an output. But we can also search terms that are somehow related, for example, to water quality. For example, here heavy metals, and we actually get a list of different heavy metals that could be used in the search. So, in conclusion, the AquaInfra ontology search provides related term search to the AquaInfra interaction platform metadata searches. The integration work of the ontology search to the AquaInfra interaction platform is currently ongoing. This is done by our German colleagues from 52 North, and they said to me that it's almost finished, but not quite yet. And this work was done by using the GEMET thesaurus data. We could use also other ontologies or thesauri, either individually or together with the GEMET data. And this would require some customization of the SPARQL queries. And this service could be made easily to support also multiple languages. Okay, thank you for listening.